Hello everybody. So in this video I'm gonna go over example 3.3 of Griffith. I'm doing this again because I haven't done it in a while and I want to see how I can do it again, and also want to show what is my thought behind it and if I can get it correctly. And I think I can help some people see how to uh, think about this problem. So I already drew uh, the drawing, the picture, and I know that I have V equals to 0 at the two plates on top and V naught on the plate on the left. These plates are infinite, so they keep going in every direction. So now one thing that I know already is this V naught. I want to start from this. So I know that V is equals to V naught when X is equals to 0. Now, I know I have these other two, but I remember that the boundary condition will always be in couple. So if I said that something will be dependent on x, it means that I will have another boundary condition dependent on x. So let me see what I can do. Oh, I know that on this side is going to be equals to b naught on the left, and I know that I have to find it on the other side. Most of the time, these boundary conditions are mirrored, so it's either at 0 and then infinite, negative, infinite, infinite, or 2 points are parallel to each other. So I'm going to say that v, when x approaches infinity, v approaches 0, because of course it's getting farther from the left plate. Now instead, v is equals to 0 when y is equals to a, because we know it for the drawing, and also v is equals to 0 when y is equals to 0. So these are our four boundary conditions. So I'll say 1, 2, 3, 4. Now remember that there are going to be 4 because it doesn't depend on z, as z has nothing to do with the voltage, and this means that um, I'm going to have 4 conditions. As I said, always 2 couples of condition, always coupled conditions. So for example, if we had any condition on z, it means that we had 2 conditions on z. All right. So now I remember that Laplace's equation in this case has to be in 2. Actually, I'm going to say the voltage, which is in terms of x and y, t I remember is going to be equals to 2 functions multiplied together. I'm going to say capital X in terms of x and capital Y in terms of y. So as you can see, I have v in terms of x and y of two functions. Now I know that the second derivative of v in this case will be in terms of x and y. So I'm just gonna say r just to make it easier, faster actually. Is going to be equal to 0. So it means that the second derivative of x in terms of x, of course. Actually, if I take dv, second derivative of v, in terms of x, then plus the second derivative of v in terms of y, I know it's equals to 0. So I save some time for nothing. So if I take the first one, the first one is just going to derive the capital X because it's the only one that is in terms of X. So I'm just going to get a capital Y in front. So capital Y in front, small y. And then d squared x, capital X over the x squared, okay? And then the second one works for the second one as well. So if I derive the second one, it will only be derived in terms of the y component. So the x component will stay the same. So I'm going to have the x component right here as a constant front, and then the second derivative of our y component. And I know that this has to be equals to 0. Now I can divide both sides by v, so I can divide both sides by this value over here. Divide these sides by this, and then divide this side by this part as well. This means that I can cancel out x and x here, and this y and y here. So I get that this is gonna be equals to, I'm just gonna copy stuff, it's just easier, faster to rewrite them. Okay, so we're gonna have on the first one 1 over this value right here, and then times this plus our value over here, which is going to be equals to 1 over capital Y, and then this value over here then is equals to 0. Therefore, I know that these two have to be equals to each other. So I know that, well, actually the opposite of each other. So this has to be equals to negative of this right here. So let me take these two separately. I know that these two both have to be equal to a constant. So I know that this part over here will have to be equals to a constant. So I'm going to call it k squared to make this calculation just easier. And then this value over here has to be equal to the same constant because we said they're the same thing. So it's equals to k squared as well. K squared as well. I can just move the negative sign on the other side, so negative k squared. Perfect. I can treat this actually. I can multiply both sides. In this case, I multiply the left and the right by this. So here I cancel out the capital X's. And here, multiply both sides by this. I can pull out the capital Y's. And then from the first one then, I'm actually going to rewrite this better over here. And this one better over here. Okay. From the left side, we're going to get, I'm going to actually write X, or capital X, in terms of X, double prime, is equals to k squared and then capital X. As you can see, this is the differential equation, second order. So I'm just going to say that r squared is equals to k squared. So that r is equals to plus or minus k. Okay, so I solve this left. I go to the right, I happen to have the same thing. So I'm going to have this capital Y double prime on the left is equals to negative k squared times this capital Y. So as again, differential equation. So r squared is equals to negative k squared. It means that r is equals to ik. Perfect. So now we know that in this case we would solve it as e at the power of I k y, because in terms of y here, and here would be equals to plus or minus kx. Now if I go back here, I can solve this, because I know that through Euler's formula I can solve this, and I get that is equals to cosine of ky plus I sine of ky. But one thing is that I want to have constants in front of this. So for example, I want to write constant d over here and c over here. Of course, these two together, I is a constant, so I can just recall it again d. So I'm just going to delete it and call everything d. And on the other side, that we're going to get that is equals to a e the power of positive kx plus b e the power of negative kx. Okay, so now I have voltage. Again, we said in terms of x and y is equals to, well, capital X, which is equals to this, now we said, times our capital Y, which is equals to this instead. Perfect. Now we can start applying our boundary condition. Let me just take this and move it down here. I'm going to start from the first one. We said the first one is going to be equals to b equals to b naught when x equals to 0. So let's go back here. Actually, that's I remember that's the last one. We always want to find when something is equal to zero. So, for example, let's take the second one. When x approaches infinity, b approaches zero. So I'm gonna go here. Given by the second boundary condition, b of infinity, comma y is equals to. Well, if we were to graph, we know that e in the power of positive x. Let me just see. Okay, it's gonna go up to infinity. This value over here goes up to infinity, so we have to stop it from going up to infinity. Therefore, we have to say that. Actually, I'm gonna say that equals to infinity plus. Well, this value will be equals to zero when x approaches infinity. I'm gonna write an a in front. A infinity plus b zero. And then the y doesn't change, so it's the same. Okay, and now of course I want it to be equals to zero. It said. So therefore, this b value is fine the way it is, but this a value actually has to be equals to zero in order to cancel out the infinity. So we already found the first part. So we know now that b of x and y is equals to b times e the power of negative kx times, well, the rest. So this power here. Now let's go back to our boundary condition, and we have that v is equals to 0 when y is equals to, actually I'm going to use the fourth. V is equals to 0 when y is equals to 0. So I'm going to say, given by our fourth value, boundary condition, v of x comma 0 is equals to 0, and there is also equals to, well, let's take what we have over here, and let's change our y into a 0. So 0 here and 0 here. Now, as you can see, this sign goes to 0, so we have no problem. But this sign over here goes to c. And of course, we have then to put c equals to 0. So now our new boundary, formula for x, b, or x and y is going to be equals to b e to the power of negative kx times d sine of k, what's that, ky. There we go. Also, now we're multiplying two constants, so we can just call one single constant. So we just copy this part over here. I don't want to rewrite it. It's gonna have, let's just say b. Actually, not a whole new constant. Just call it e. And we said it's equal to b times e, but it's just constant. We don't really care. Times e to the power of negative kx times sine of ky. Perfect. Now let's go back. This is our third boundary condition. We know that v is equals to 0 when y is equals to a. V is equals to 0 when y is equals to a. So let's rewrite it as, given by our third condition, boundary condition, v is equals to 0 when v of x comma a is equals to 0. So therefore, this value has to be equal to 0 when we substitute a for y. Okay. The only way we can do this is by bringing this sine value to be equals to 0. So sine is equals to 0. Sine of, let's say, ka is equals to 0 when ka is equals to n pi with n to be equals to 1, 2, 3, and so forth. Because of course, when we are along the x-axis, the sine value will equal to 0. Therefore, k is equals to n pi over a, as you can see. So let's go back to our formula. Now we know that v of x and y is equals to, what is that, e as a constant in front, times e to the power of negative kx, and k now we know is equals to n pi over a, x times sine of, again, n pi y over a. Okay, so now we found our formula, and we only have one last boundary condition to include. The v is equals to v naught when x equals to 0. So let's go back here. It means that when when x equals 0, so 0, y, our thing is equals to v naught. So this has to be equals to, but when I have e, and then e to the power of 0 is equals to 1, so I'm just going to skip it, times sine of that. Okay, so now we've used all our, I didn't write down, it was the fourth boundary condition. So now that we use all four boundary conditions, we found a general solution for all this. So of course, this has to be because for all the values of n, because we decided n is equals to multiple values. Therefore, we can say that v is actually going to be of x and y is equals to a sum with n is equals to 1 to infinity of our Cn times the sine of n pi y over a, pi y over a. Oh, sorry, the book uses Cn. I used E, so we could write it as E, doesn't matter. I'm just going to use Cn because it's better for Fourier series. Okay, so Cn 1 is equals to, we said, V naught. Okay, so how do we solve this? Well, we have to integrate this, and we can use it using Fourier's trick, if I recall correctly. There's something is equals to this part over here, actually. And the integral from 0 to a, because it's the boundaries, of this sine over here, times the sine of something very similar. So sine of the same thing, but with n prime. dy is equals to, we multiply both sides by this sine of n prime, 0 to a of v naught times this sine of n prime pi over y over a, always do y. Then we get that this left side, so this integral on the left side, okay, found it, is equals to different values depending on the value of n prime. So if n prime is different than n, then it's equals to 0. If n prime is equals to n, then the solution is equals to a over 2. Okay. So now we remember that we were talking about a series right here, right? But we just said that if it's anything but equals to n prime, then it's equals to 0. So we can just get rid of everything. And we find out that C of n, in this case, because we decided we can replace this value, this left side, by this value over here, because we said they're equal. So we would have something like C of n of, we just said a over 2, yes, a over 2, and we're down, okay, of a over 2 is equals to, well, the right side instead. We didn't solve, so it equals this value right here. And of course, since now we don't have any n's, this n prime becomes n. We don't need to care about it anymore. And therefore, C of n is equals to now 2 over a of this integral right here. Okay. So we can solve this. We know that b naught is equals to a constant, so C of n is equals to 2 b naught over a of this integral, which is equals to a over n pi times negative cosine of n pi y over a from 0 to a. So here I can start this a over here. Alright, so equals to 2 b naught over n pi times, we just said, negative cosine of n pi, because we just substitute the y, you cancel out the y at the bottom, minus cosine of 0, actually plus, because minus, plus 1, because cosine of 0 is 1. So this is our solution. And again, we can think about this as our n changes. So this thing is equals to different values based on the n. So if n is equals to, if n is even, so 0, 2, 4, whatever that is, then we're gonna get it equals to 0. I'll put it first. It's equals to 0 if n is even, and it's equals to 2 if n is odd. Perfect. So now we can just avoid the 0 because we don't need it. So if we go back to our solution of this b right here, let me just copy and paste it. I don't know what this. Okay. So now we know what is our C of n, and we can rewrite this as the addition of the sum with n is equals to even, so 1, 3, 5 to infinity of our C of n, which we just said is equals to 1 second. Okay, I can solve the C of n, so it is equal to 2. So it is equals to 2 is the parenthesis, so there will be 2 times 2 v naught over n pi, because I was thinking about the 2 as only the answer from the parenthesis. So we're gonna have 4 v naught over n pi times sine of n pi y over a. Let's see. This should be our solution. And we check with the book. Let's see what the book says. Okay. We missed an e to the power of something. Oh. Yes. Now I see what I missed. Over here, we were over here, and then I just ignored the e to the power of. So actually, in here, yeah, it's b equals to naught. That's why I was thinking about this, because we said it's equals to naught. So e to the power would be of negative n pi over a of 0. So that's why we got this 1. But the general solution is still contains this e to the power of n naught n pi over a times x. So here I have to write e to the power of negative n pi over a times x. And this should be our mistake. Yes, that's the only thing I missed. I just recopied the final solution and the wrong solution, but everything is correct, so I'm not worried about it. Okay, so that was my way of solving it again. One other thing is that to be honest, I had to look up what was the integral of this sign, this Fourier trick, because the book just says using Fourier trick. We use this, but to be honest, I couldn't solve this on my own. I had to use the help of the book, but except for everything else, I think I did pretty well. Now I forgot the end, the solution. That's just because I wrote here wrong. Because here, as you can see, I wrote x, and then I wrote x, and then I changed it to y to 0. Instead, I should have gone here. I should have actually written a general solution would have been b of x comma 0 of the sum, and is equals to 1 to infinity of cn e to the power of negative n pi over a times x, and then sine of n pi y over a. So that was like our half solution, and then we had to plug in our initial, the first boundary condition, this very first one right here, and that's how we got the c of n, the c sub n, sorry. And that was it. I hope it helped you guys, especially hearing the thought behind it. And let me know if you have any question in the comment.